Hey everybody, this is Mr. Chernetsky, and this is Geometry Unit 1, Lesson 5. We're starting here with our jump start, and the question is, which one doesn't belong? And the fun thing about this exercise here is that if you think carefully, you could find a reason why all four of these would be the one that doesn't belong. Now the obvious one is D, the triangle, because it has three sides, while the others have four sides. But we could even come up with a different reason, like a less obvious reason. And one that maybe I will use is this one has a sum of angles equal to 180, while the quadrilaterals, the inside angles will add up to 360 degrees. So that would be a less obvious reason why D doesn't belong. A reason why the rectangle wouldn't belong. Well, the most obvious reason is that not all sides are congruent. Okay. The rest of those all have congruent sides. For the rhombus, that is the only one where not all the angles are congruent. So that would be your argument why the rhombus would be the one that doesn't fit. And the square, it's a little tricky, but kind of leads us into what we're doing today. And this is the only one that has more than two lines, or sorry, more than three lines of symmetry. Or it has the most lines of symmetry. There are some other reasons we could think of why a square would be the one that does not fit, but that is the one I'm going to go with because it kind of leads into what we're talking about today. So for each of these shapes here, we're going to talk about lines of symmetry that reflect the quadrilateral onto itself, and then we're going to talk about rotational symmetry. Now in class we can do this with patty paper, but to help us out in this video, I'm going to use some GeoGebra models here, okay? Now what I have in this GeoGebra model is I have a rectangle or a quadrilateral here, which we'll change the shape of. And then this red dashed line is a line of reflection. So if I move this guy, our reflection will show that, okay? Now, what a line of symmetry is if we were to reflect it, would the shape land on top of itself? Okay. So a obvious line of symmetry would be going horizontal. So I'm just going to take our line of symmetry and line it up along this horizontal, and we can see that at that point the shape would reflect along itself. So one line of symmetry is going horizontal for the rectangle. Another line of symmetry would be if we went vertical. So we went directly down the middle. There we can see it'll line up perfectly. So there's our other line of symmetry on the rectangle. Okay, so two lines of symmetry so far. All right, a common guess of a line of symmetry is, what about if we went diagonals, like corner to corner? Could we have a line of symmetry going that way? Well, let's see. Let's move our line of symmetry. So So that's on the diagonals. And as we see here, no, the diagonal does not work. Okay, so the diagonals do not work as a line of symmetry. Okay, get this cool kind of mirror image, but it's not reflecting on top of itself, so that would not work. Okay, let's move our reflection line over here again. And let's move on to the next shape, which is a parallelogram. Now to make a parallelogram, all I'm going to do is I'm going to take my rectangle and just kind of stretch it out a little bit, and there's my parallelogram. And now let's see if we can find any lines of symmetry. Okay, let's try horizontal, like we did with the, or like we had with the rectangle. So if we go horizontal, nope, that doesn't work. Okay, doesn't quite land on top of itself. Vertical, let's see. We go right. Vertical is also not going to work. Okay, but what if we did like a slant, like we went a line going this way, like slanted? Let's see if that'll work. Get it lined up. Nope, that doesn't work either. Okay, cool image doesn't, not a line of symmetry. Okay. And that is the thing about parallelograms, is that there are no lines of symmetry. No place I can put that line to make it work. Okay, let's move our line of symmetry out of the way here. Okay, a rhombus. To build our rhombus, we're going to use some Pythagorean tricks here. So I'm going to put B right there, and then I'm going to move this so that it is going 4 over and 3 down, because that way I know that this diagonal here by Pythagorean theorem is exactly 5 units long. And then if I did the same thing with A, we can go 4 over and 3 down. Now that side is equal. And if I just move D, so we have that same 3 by 4, all the sides now are exactly 5 in length. Okay, so let's try our line of symmetry. So one thing we might do is go across our diagonals. And the vertical diagonal works. What about the horizontal diagonal? Yep, that works. Okay, so 2 lines of symmetry. So across vertical and across horizontal. And that is going to be it. So we can't go across like that. That doesn't work. So nope, those are the only 2 that will work for the rhombus. Okay. Let's try a square now. So for the square, we'll make all the sides the same and all of the angles the same. In other words, 4 90-degree angles. There we go. All right, let's try horizontal. That works. Horizontal works. What about vertical? That works. What about going diagonal? Diagonal works as a line of symmetry. And the other diagonal works as well. So 4 lines of symmetry for the square. So we can go vertical, horizontal, and diagonal. All 4 of those work. And those are lines of symmetry. Now, for rotational symmetry, if we were to spin our shape around a center point, how many degrees would we have to go before our shape would land on top of itself? So we're going to try another GeoGebra. Again, this is something you can do with patty paper. You can trace it and spin it and see. Let's go ahead and go to our GeoGebra demonstration. Okay, here is our rectangle. And let's see when we spin it. Spin, 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 spin. And at 180 degrees, it spins and lands on itself. Okay? And then it doesn't land again on itself until we've spun it a full circle. But we don't really count a full circle as rotational symmetry because everything, if you spin it 360, is symmetrical at that point. So 360 doesn't count. So we only have the 180 for our rotational symmetry for the rectangle. Oops, that. 180 degrees. Okay. Well, how about the parallelogram? Let's try that one. So let's make a parallelogram. We'll shift those 2 over so we get a nice little slanted shape. There's our parallelogram. Let's try it again. So spin, 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 spin. And at 180 degrees, we line up. And that is it. Okay, so only the 180 is the only rotational symmetry that we have. Okay. For the rhombus, let's build our rhombus. See what happens. Okay, using our trick, we're going to go 4 over and 3 down. Okay. 4 over, 3 down. And for both these, 3 down, 4 over. So there is our rhombus. Let's try our rotational symmetry. And once again, it's 180. And then that's it. We don't get rotational symmetry after that. All right. And our last one is the square. So let's make our square. Go. Nice 4x4 square. Okay. All right, let's do our rotation. So we're spinning, and the first rotational symmetry we have is at 90 degrees. And if we keep going, after another 90, oops, too far, 180, there's a second rotational symmetry. And if we keep going another 90 degrees, too far, at 270 would be our third rotational symmetry. So 270, 180, and 90. Degrees, 180 degrees, and 270 degrees. And that's our rotational symmetries. Okay. Consider the set of quadrilaterals that are trapezoids with exactly one pair of opposite sides parallel. Is it possible to reflect or rotate such a trapezoid onto itself? Okay, so let's draw our trapezoid. Okay, if I have a trapezoid that looks like this, is there any rotational symmetry? Nope, no rotational symmetry. Okay, so that doesn't work. What about lines of symmetry? Let's don't think so. So there's no line here that I could draw to have this shape line up. It's just not going to work. So it doesn't have any lines of symmetry. So standard trapezoid, no. But what if we made a special kind of trapezoid? Known as an isosceles trapezoid, where these two sides are equal. So let's see. So let's move this guy over. There we go. There's our isosceles trapezoid. And let's see. You can visually see that horizontal is not going to work, but I think a vertical just might be possible. Yep. So if you have an isosceles trapezoid, you could have one line of symmetry. However, still, you would not have any rotational symmetry, as we'll see here in just a second. So our isosceles trapezoid still has no rotational symmetry. So one vertical for the isosceles. Okay. No rotational symmetry. All right, let's talk about some other polygons. Ready for more. Can you draw a quadrilateral that only has one line of symmetry? Well, we have just done that. Okay. The isosceles trapezoid. That only has one line of symmetry. Can you draw a polygon that has three lines of symmetry? Well, something we looked at the start of this was our equilateral triangle. It doesn't quite look equilateral. Let's see if we can do a little better one. There we go. Nice equilateral triangle, which would have lines of symmetry through each vertex. Through the other side. Can you draw a polygon that has a rotational symmetry of 40 degrees? Okay, this is a little tricky. But let's just think about this. If we had rotational symmetry at 40 degrees, well, we would go, one turn would be 40 degrees, another turn would be 80 degrees, then 120 degrees, then 160 degrees, then 200 degrees, 240 degrees, 380 degrees, oh, no, not 380, 280 degrees, and 320 degrees, and finally all the way around to 360. So how many turns is that? That's 1, 2, 3, 4, 5, 6, 7, 8, 9. That is a 9-sided figure known as a nonagon. And if you want to know what that looks like, it's kind of tricky to draw. We'll have we want a regular polygon. With 9 sides. And there there's what a 9-sided polygon would look like. Okay. And just to verify that this would rotate at 40 degrees, let's put our center in there. And then we will rotate.
Hey, I got peaches for you.
We're going to rotate and we want to get this the same as my there we go. Let's see if this will work. Okay, so rotating, kind of hard to see here, but let's see, at 40 degrees. There we go, exactly. And every other 40 degrees it will line up as well. So that is how we would do it. Okay. Our takeaways. So the shape that only has a 180 degree rotation and no lines of symmetry, that is going to be our parallelogram. Okay. And then under that we have some subcategories of parallelograms. So something that has a 180 degree rotation but 2 lines of symmetry through the diagonals, that is going to be our rhombus. Right? If we go back up, there's our lines of symmetry through the diagonals. 180 degree rotation, but 2 lines of symmetry, but not through the diagonals, through the midpoints of the sides. That's a rectangle. And something that is considered both a rectangle and a rhombus, that is a square that has 90 and 180 degree rotation, 4 lines of symmetry. Those are our shapes that we're working with today. Okay. Okay, notation. So if we are using, if we are representing an actual line segment, so something like that, okay, we would represent that notation as the 2 endpoints and a little bar above it. However, if we were just talking about how long AB was, like if it was 5 centimeters, we would say, we would use the notation of the 2 endpoints but without the bar above it. Okay? So therefore, if you're talking about an actual geometric segment, it's AB with a bar. If you're just talking about a length, it is AB without it. If 2 line segments, say AB and CD are the same length. Oops, not CD, CD. So suppose CD equals 5 units as well. Okay. In other words, we can move them, rotate them, and they'll land on top of each other. We'll say that they are congruent, and the symbol that we use for congruent looks like an equal sign with a squiggly. However, if we're just comparing their lengths, we will just use a regular old equal sign. Okay. This will get more used to this as we go along and we start talking more and more about congruence. Angles. Angles are represented by the angle symbol. And if you have a single letter there, we can call that angle A, like so. Or if we have 3 letters, 3 points that we're working with, we could call this angle CAB. And the key thing is that the vertex is in the middle. Okay. So for example, we could also call that or angle BAC. Okay. Now, if I want to talk about the measure of an angle, okay, some degrees, so that was like 45 degrees. We'll put a little m in front of our angle, so we would say the measure of angle CAB equals 45 degrees. So that little m means measure of. Okay, we've talked about congruence, diagonals, lines of symmetry. We identified different types of quadrilaterals. We talked about some regular polygons like an equilateral triangle, trapezoids, rotational symmetry. Let's go to our retrieval. Okay, some vocabulary. So a polygon with 5 sides, we call that a pentagon. A polygon with 6 sides, we call that a hexagon. And then a polygon with 8 congruent sides, so if all the sides are equal, we use the word regular. So we would call this a regular octagon. Okay. All right. A little bit of algebra review. So we have a table here, and we're asked to describe the line that is that table. So they're already telling us that this is a linear graph. Okay. To verify that, though, we can look at how our x and y are changing. So our y is going down -3. Right? Every time it's going down -3. And our x is going +1 every time. So the slope of this line is equal to -3 over 1, or just -3. All right, next thing we need to write an equation, we need a y-intercept. And we can see that on our table because our y-intercept is going to be right here when x equals 0. That's our y-intercept. Okay, so y-intercept equals -1. So our equation is going to be y equals -3x minus 1. There is our equation of that line. Okay, a line that is parallel means same slope. So it's going to have the same slope, -3, but it's going to have a different y-intercept. That's going to be at 6. So our equation becomes y equals -3x plus 6. And finally, if a line is perpendicular, that means we have opposite reciprocal slope. So instead of 3/1, it's going to, or sorry, -3/1, it's going to be a slope of +1/3. Okay? Flip that slope upside down and change the sign. And again, our y-intercept is still at 6. So our equation would be y equals 1/3 x plus 6. And that is it for this lesson.